Caroline Fresinet is going to go ahead and kick off this session as the chair. Go ahead, Caroline.
Thank you. So welcome to the overview talks, number 2, planetary measurements needs. And we have 3 talks in this session. And the first one will be given by Team Titus. And if I understand well, Serina, you're also talking in this during this talk. You have 25 minutes talking about planetary, aeolian, and meteorology, and we'll give 2 minutes warning. And let's try to keep a couple of minutes for questions at the end of the talk. Go ahead.
All right, thank you. So I've got part 1 of this 2A overview talk, and this is primarily focusing on what came out of the 7th International Planetary Dune Workshop that was held in Alamosa, also virtual last month. All right, this is up there. Did you do that? Okay. This may not be. All right, so when we started planning these workshops for this summer, Serina and I agreed that this would be sort of a pair with the Alamosa workshop being the first and then this one being the second. But in putting this presentation together, I realized there was actually a 0th workshop that started this whole process. And that's the one that's in the 6th International Planetary Dune Workshop. It was completely virtual due to the pandemic. And the focus there was facilitating submission of white papers to the decadal survey. And so Serina already showed some of the decadal survey questions that include aeolian processes. All right, so there were several decadal survey white papers that went in over the 2 years. Of course, the decadal survey met and now they've got it published. And then, of course, the meeting last month, lots of group discussions, some discussion about the decadal survey, but also focusing what should our goals be, our objectives, leading down to investigations. And then today, we'll be talking about measurements to some extent, but mostly mission concepts as we move forward this week. Next slide. All right, so during last month's workshop, the focus was on science. It mostly aligned with what came out in the decadal survey. There were several white papers, like I said, that had moved forward from the 2020 workshop. And then we also looked at what's the synthesis output from the decadal. So the goal was a goals document, which is still, of course, in progress. And I'll be mentioning that a little bit on the next few slides. But one thing that we noticed was the goals document draft that we submitted as a white paper was lacking a goal. And I'll talk more about that a little bit, but it was the physics of dunes, the physics of ripples. And so I think it was a very useful workshop just for that alone. Unlike this workshop, the first one was really driven by what was submitted as abstracts. And so the sessions were organized that way. So from the bottoms of the oceans to the outer solar system was the opening session, just to describe the vast variety and locations across the solar system that we see aeolian-like features. Then we went into essentially all the ways you can move sediment, sliding, the sediment budgets, going into then dune dynamics and winds, and then of course the great sand dunes, both from a science point of view, but also exploration. Our visit to the Great Sand Dunes ended with an evacuation due to a wildfire. And if Brian, I think, has some great movies of the wildfire version of a dust devil. So saltation and then dune migration was the next day, followed by ripples, mega ripples, transverse aeolian ridges. And then we concluded with landing site characterizations and off-world in situ studies. So great lead off into this workshop. Next slide. All right, so the goals document, it is still in a state of flux. However, I think we can agree on probably 5 goals. Wind or climate, environment, fluid properties, most of the time we think aeolian, that's air, but in some cases, water might be a better analog fluid. And then sediment. So you need wind, you need sediment to make dunes and ripples. So on the sediment side, what's the composition, the geology, the source? Where did it come from? Where's it going? What does the bed form look like? Is there a sink? And then the physics. What are the physics going on right there at that interface between the air, the wind, and the dune surface or the ripple surface? And then what comes out of that? Are there hazards? What are the risks? And then are there mitigations for those risks? Or in some cases, the wind provides a mitigation strategy itself. And then life. Does aeolian processes pose a niche in terms of astrobiology, either present or maybe preservation of the past? Next slide, please. Oh, yeah, switch back. Also took a look at cross-cutting themes, at least one, interactions with other processes. So pun intended, aeolian processes do not occur in a vacuum. Actually, sometimes they appear that they do, but there's a lot of interactions with other processes, water cycle, for instance. And so that's something to keep in mind. All right, next slide. All right, so topic 1 or question 1, goal 1, depending on how you want to look at it, was the wind or the climate. So this is really focused on the fluid that's causing the movement, broken down into 3 different objectives. Or questions? What are the physical conditions or processes that control these landforms? What is the history that's recorded there? And then identifying any relevant analogs. And this could include wind tunnels as well. So next slide. I'm going to skip through these relatively quickly as I only have 10 minutes and I'm probably halfway through that now. Topic 2, this is focusing on the geology, or the sediment itself. Understanding sediment facies and architecture is key to the surface processes. So these are the dune scale processes. Then we can move down here to dune construction or the basin-scale. And then how are the aeolian features and phenomena incorporated into and preserved in the geologic record. And of course, Utah is wonderful, lots of fossilized dune fields. That's showing us a record. And then determine aeolian erosional rates for different geologic materials. Why does Titan have so few craters, for example? And then the stickiness or immobility of the grains. And is that due to volatiles or salts, or maybe it's the nature of the composition? Our organic grains on Titan sticky, for example. Next slide. All right, dynamics. This is the new one. So what are the thresholds for transport? What are the controls on saturation length and drag length? This was definitely focused on a lot at the last workshop. What are the time scales? And what are the spatial scales, and how does that change the physics? Next slide. Life, habitability, and or astrobiology. So how might aeolian processes contribute to the formation and maintenance of habitable niches for extant Martian life? And can aeolian processes preserve evidence for extinct life? And so I'm not going to go into the details here, but like I said, 10 minutes, I don't have the time to go into the double of the details. All right, next slide. And then hazards. So what hazards? Increase our capability to predict and model environmental aeolian hazards. Increase our capability to access aeolian-derived or modified landscapes in order to reduce operations or mobility risk. In other words, let's not get stuck in the sand. And then can wind or aeolian processes be used to aid in exploration, not just the hazard avoidance? So winds, could they be used as power? The winds or dust devils, can they be used to clean solar panels, for example? And then what's the likelihood of forward contamination by aeolian processes? So we take bugs on our spaceship to Mars. Does the wind blow those bugs downwind? All right, next slide. All right, so you could take a look at this all as a sort of a science traceability matrix. So just example questions, and then what are some of the measurements that we might need? And so I started writing this out and realized this looks like one of the quizzes my 10-year-old daughter takes at school. So I think in reality, that's where we're at too. We're taking a quiz today. So on that note, I will hand the mic over to Serina.
Thank you, Tim. Switch to my slides. Yeah, new slides. Okay, while he's pulling that up, the basis of the list of measurements I'm going to show is from some discussions that we're having, some telecons. We pulled in a group of about 20 scientists working in different areas of aeolian and meteorology focused, primarily planetary, but not entirely, and have basically given them the task of, okay, if we were going to actually investigate specific things, what measurements do we need? And of course, they come back to me with a long list. And I say, okay, no, what do you really need? Like, what's the minimum you need before you wouldn't fly the mission? So I'll show the list is still being worked on, but it's a good starting point for our discussions. Yeah, that's the right one. Sure. Okay, cool. Got it. All right, thank you. Oh, let me go back real fast to acknowledge the many people that I've been working with on this. So a lot of really great discussion, and the aim is to generate some review papers too that will summarize all of this. All right, so we focused in 4 areas, and these aren't so much a specific investigation, but a determination of a particular parameter or idea that is really a basis of a lot of the models that we use to interpret what we see on other planets. So surface roughness, understanding connection between the turbulence and the macro scale of vertical wind profile, characterization of the saltation layer, and the threshold for grain transport. All of this is with the aim toward, again, as the point I raised earlier, when you're doing in situ measurements, it's not, I want to understand this one place and this one period in time really well. It's how do I calibrate them, use this to calibrate or develop a model that now I can apply other places where we don't have the in situ measurements. And yeah, the presented list is not necessarily the final one, but it's a reasonable starting point for this workshop's discussions. Okay, hold on a moment. We're trying to get the Zoom caught up. Perfect. Okay, so some key considerations that kind of apply across the board is, of course, we desire really high frequency measurements during events. And then there are other times where we don't need it as high frequency. And we'll have discussions on Thursday about how you might do operations in order to capture events. We need thinking about landing site or observation site, sorry, you need a simple enough site that you can match what you're doing and measuring to a model, right? If it's overly complicated, we'll get some great observations of that site, but how do you extrapolate from that? You need a simple enough site to do that. And for many of these investigations, we thought we would benefit from a fixed location through a long temporal baseline, be able to watch the diurnal and seasonal cycles and perturbations. But even if we generally don't need to move, there is some thought about initial optimization of your placement within an area and your orientation. And that's something that we should all discuss when we're in the field and on Thursday, because how important that is may dictate how hard we can push the engineers. Having a one-time motion is hard. It's easier than doing lots of motion, but it still is, it adds quite a bit. The more times you have to move, the harder it is to design it, design the spacecraft. And unfortunately we can't just send the human there and pick it up and move it. And then as we saw with some of the terrestrial presentations this morning, instruments need to be robust to get to the observation site and then operate within the environment. Again, we can't go there and dust it off or reposition it or change out a sensor because the saltation that we were measuring has now damaged it. Can you click on it? Can you click on the slide? Thanks. You have to click on, I think. All right. So starting with surface roughness, this is a parameter that is of big importance because it appears in a lot of the models that we use. We use estimations of Z0 in climate models. In that case, it's, the grid cells that they're using can be kilometers in size, but they're applying a particular assumption of surface roughness. But that's really important because it leads to the estimations of dust lifting and such, which dust is a major contributor to the Martian climate, as well as other planetary bodies. It also appears in models of wind shear and saltation dynamics, but again, now we're talking small scale. So that's been one of the discussions is how do we take very localized in situ measurements? How do those possibly relate when we want to compare those to the models? Shown here are some typical terrestrial Z0 values, and ones on Mars have found to be generally pretty similar, with the one time it's been actually measured with Pathfinder. Overall, it really relates to the size of and spacing between the roughness elements. And this is one of the other areas where this is important is if you can estimate, you can do it either direction, right? You can try to estimate Z0 and that tells you something about the surface roughness, or you can try to measure the surface roughness and then approximate what your Z0 parameter should be. Another area where this could be really useful is Z0 itself, this inherent quantity that we use to kind of look at how the wind shear, as you have this wind coming in, right, how it changes as you go down to the ground, the law of the wall. That assumes that that sort of parameterization works. So one possibility is if you're able to very confidently and carefully estimate Z0, you could actually test this model, because if you get an unphysical number or you can't derive it at all, that's an indication right there that this parameterization does not apply for that planetary body. All right, so here are the measurements that we're looking at. I'm going to provide folks on the field trip with a one-pager printout of this, so I'm not going to go through it in detail, but you can kind of get a sense of baseline idea. We want to connect wind measurements with the overall topography, thinking about basically all the sources of the surface roughness. In the threshold, it's more of we're kind of assuming the model works, and we just want to characterize it and calibrate it well enough. So that's kind of how that's divided here, and I've highlighted in red the differences between kind of a baseline and a threshold. Some other considerations are Z0 will change whether or not you have saltation going on. So it might be really important to know whether or not that's happening at the time. And you need a sufficiently long upwind fetch so that you are kind of developing these aerodynamic properties into something a little more stable. Okay. Yeah. Okay. Sounds good. All right, so it's for turbulence characterization. Turbulence is really important because all atmospheric processes involving energy, mass, and momentum are connected to the parameterization that we use. So in this case, we're looking at how all those turbulent eddies across multiple scales are moving energy and mass. And then we've parameterized that into kind of a more macro scale model, right? So this is the law of the wall and such. That model has been developed and tested and calibrated for Earth, and it works really well for Earth, although in individual places, depending on your level of accuracy needed, you want to calibrate it for your particular place. It's never been tested on another body. And there are reasons to think that it may not work. For instance, on Mars, since it's not necessarily what is neutral atmosphere, but it's used. We use it for EDL predictions. We use it to connect the few wind measurements we have to a general idea of what the wind shear may be at the surface. We are constantly using this particular connection. It's never been tested. So that would be a really, I think if we tested and showed it worked, that would be certainly very interesting, but it wouldn't really change much of what we're doing. But if we showed it didn't work, that would be huge. So the measurements needed in this case is trying to measure the different fluxes. And then if you actually really wanted to get to turbulence closure, you need to do the direct characterization and also measure your mean atmospheric state. So that broader scale, macro scale system to actually make sure that they're connected in the same way that we expect. So shown here, baseline measurements again and threshold, getting the wind measurements, air temperature to understand that energy transfer, air pressure, and then radiation estimates as well. And then in the baseline has the CO2 abundance also. So you're looking at the atmospheric pressure and its slight variations through the Martian day. And this is like Mars focused. For saltation, we're looking at how much and which grains are getting moved at different heights and with which speeds. In general, this is an area where we found that the models are pretty good. So we generally are looking more at, sorry, talking in the wrong slide here. The models are pretty good. And so we're generally looking more to calibrate them than we are to test them. But this is really important because models of sand transport feed into things like estimates of erosion and dust lofting. So yeah, here, focuses on calibration. So this is an area where you can maybe have a few more discrete measurements and you want to calibrate it rather than be developing the model. In this case, you want to connect drivers with the response. And so for the threshold, at least one of these, ideally you measure more than one of these, so you get a fuller picture of what that saltation layer is doing. And of course, we're all talking vertical profiles here. It would be really nice to understand the horizontal variation that's happening. For instance, if you have a sand streamer. Key points here are you need to be watching while it's happening, ideally watching the saltation layer develop as well as its saturation. So that's very time-specific monitoring. Grain lofting and lifting is quite different. We don't have very good models, especially when it comes to dust lofting. This is a very key open question in planetary science. And as mentioned before, this is a very important parameter used in many meteorological and climate models related throughout the history of Mars. So for instance, even ancient Mars, we want to understand how the water has been lost from the atmosphere. Apparently, dust plays a key role in that. So like there are so many parts where understanding the dust cycle on Mars is really key. So here's the different measurements. Aim is to control the motion initiation and the dust and understand how that's working. Thank you. So wind, understanding some of the energy, the turbulence and such, and then characterize the grains that are moving. In the threshold, it's more at the scale of, again, we're assuming that we understand how the wind changes with height. So just a couple measurements to nail it down and then detect whether or not flux is going. So you're just knowing yes or no. But that would obviously be important ground truth, but much less information. And I'll stop there.
Thank you, Tim and Serina, for those interesting thoughts. We have time for some questions. If you're remote, you can either turn your mic on and ask a question or put it in the chat. And if you're in person, you can ask for the microphone.
So we have a question in person here, Carolyn.
Go ahead.
Yes, this is actually for Serina. As she was going through the talk, some of the stuff that we've done out at Grand Falls Dunefield, we've noticed that, a lot of times the law of the wall doesn't work because the atmosphere is not neutral. Fortunately, the part we care about is when the saltation starts and then, it looks really nice and we get a Z0 value. but characterization of the state of the atmosphere. So maybe even getting, and I think you mentioned in one of your slides, getting a 3D view of the wind, because we actually, while we weren't measuring the vertical winds, we saw evidence of it by our weighing Basin-scale actually being lifted. So I thought maybe you could comment on, trying to characterize how neutral the atmosphere is in trying to determine Z0.
So unfortunately, I'm not an atmospheric scientist. So I'm going to channel Alejandro and Scott, who've been helping me with this. They've mentioned that due to the very low density of the Martian atmosphere, the way in which the heat is transferred, right? You're not getting the convection. Okay.
Yeah, so on Earth, sensible heat transport is a critical part of that balance of the surface. On Mars, it's more radiative heat transport. Oh, sorry. So it's making assumptions about how those heat fluxes are being produced at the surface that aren't necessarily valid at Mars. Herman Martinez has a good review paper from the MSL era that discusses a lot of this stuff and the issues there. Carolyn, do we have an online speaker? Online question, I meant.
There are no online questions. There are online comments. So maybe either Don Banfield or Steve Metzger, you can.
This is Joel Sankey. I have just a follow-up question to that comment right there from Alejandro.
Yeah, go ahead.
Could you just expand on that a little bit? Does that mean then that I guess the way sediment surfaces dry out and the way that influences aeolian sediment transport on Mars is really different than the way sediment surfaces, wet surfaces like a wet sandy surface would dry out on Earth?
I personally can't comment. It's
Okay.
not my area of expertise. I don't know if Herman or somebody else online wants to jump in real quick. But let's go ahead and say this. Bring that question up again later in the discussions we have later this week. I think we should get moving forward because we're running a little behind on schedule. So I'm going to go ahead and switch to our next speaker. Can we? So can you, Ed Rivera-Valentin, are you online?
Yep, I'm here.
Perfect. Do you want to drive your slides or do you want us to do it?
Can I drive?
Is that fine with you? Yes.
Can you see the slides?
Yes. So our next speaker is Ed Rivera-Valentin, and he's going to be talking about how to measure liquid water properties near the surface and in the subsurface. So Ed, take it away.
Thank you. So here we're going to be talking about the type of measurements that we need to better understand active liquid processes in the shallow subsurface of Mars and other regolith interactions. I'll note that this is a huge team effort. This is based on conversations with Alejandro Soto, Herman Martinez, Jennifer Hanley, Raina Goff, Kendall Lynch, and Justin Filiberto. And it actually resulted in a white paper that was submitted to the Planetary Decadal Survey. So really what we're going to be talking about is trying to better understand the near surface water cycle on Mars. So how that water vapor is interacting with the regolith and what type of processes in the regolith are acting as sinks for that water vapor. And then when are those processes later on acting as sources for the water vapor and how is that getting exchanged back into the atmosphere? Here we have an example of some of those processes. So in the regolith, you could have physisorption, so absorption of water vapor onto regolith grains and later desorption. And we also know that the Martian regolith is very salty. And so you could have solid state salt hydration. So that's like going from an anhydrous salt phase to a tetrahydrate or an octahydrate. You could also have brine formation because you have salts there, and frost formation. Throughout here, I'm actually going to be concentrating on brine formation and what we need to better understand brine formation on the surface of Mars. First, why we're concentrating on brine formation, that is because, so if we look at the typical phase diagram for water, we're looking at temperature and total atmospheric pressure. And so that's only telling you stability against freezing and boiling. And so we see here, the first dotted line you have here is the typical surface pressure of Mars, where you would expect ice and vapor. But there are certain regions on Mars where the total pressure can increase all the way up, like Hellas Basin, where it could be up to 1400 pascals. And so that results in about a 10 Kelvin window where you could have pure liquid water stable against freezing and boiling. But note that the saturation vapor pressure just above that liquid would be something like between 600 to 1400 pascals, depending on the temperature. And we are in a very hyper-arid environment. In fact, based on the data we have from Phoenix, MSL, and GCM constraints, we can see that if we form that pure water there, it would really quickly evaporate away. And so that's what we're showing here to better understand and contextualize what the water vapor environment is on Mars. It's a different type of phase diagram. Now we have relative humidity versus temperature. The cyan space is Mars relevant combinations of temperature and relative humidity as constrained by a GCM. In the magenta, we have data taken at the Phoenix landing site. In purple, we have data taken at the MSL. In the black line, that is the ice line. So that's relative humidity with respect to ice when it is 100%. So first off, you can see that if your temperature is something like less than 210 Kelvin on Mars, you are bounded by an isobar water vapor pressure here at 1 pascals. And so, yeah, I forgot to say that all the little gray lines that you see here, these are isobars of water vapor pressure. So at night, you're bounded to have less than 1 pascal's worth of water vapor. At daytime, when your temperature is something above about 240 Kelvin, you're bounded by the 10 pascal line. So you have, if you were to have pure water stable against freezing or boiling, you have something that's 600 pascals at the best of water vapor pressure above it, and you're talking to an atmosphere that at best is 10 pascals of water vapor, you're gonna quickly evaporate away. But brines are super cool and much more stable. So as you increase the salinity within that solution, you're going to decrease the amount of water vapor that's above the liquid. That means that you are going to change the temperature at which it's going to boil, which is represented here in red. And you're also going to reduce the evaporation rate, which I'm showing you here in numbers. So as you go down this cartoon, you're increasing salinity, you're decreasing the water activity. And then obviously the more salty something is, the lower the freezing temperature is, which is represented here in blue. So the saltier something is, you could see that the cyan window, which is the space where you could have liquid, increases. So that's why we care about brine formation. On Mars, you can form brines either through melting, so salt ice interactions, or deliquescence, which is salt water vapor interaction. To melt, we have this nice map showing us how deep an ice table would be on the surface of Mars. For example, we have the Phoenix landing site where we measured it to be between 5 to 10 centimeters deep. So where these ice tables are shallow, there might be salts there, you could end up forming brines. And in fact, experiments led by Germán Martínez at the University of Michigan demonstrate that if you reproduce the conditions measured at the Phoenix landing site, and you have ice in contact with salt, the moment you are above the eutectic temperature of that solution, you end up forming a stable brine. So we were able to reproduce those conditions in lab, and we were able to see brine formation. You could also, because we're seeing all these fresh exposures of water ice, we can see likely brine formation outside of the regions where you have shallow water ice. Now, deliquescence doesn't need to be in the presence of ice. It just needs to have a hygroscopic salt in the presence of water vapor. And then at the appropriate temperature and humidity conditions, after enough water vapor has been adsorbed onto that hygroscopic salt, it will enter solution. So on the next slide, I'm going to show you a video that was taken by Jennifer Hanley. She was at the University of Arkansas at the time of this video. You're going to see the background look kind of like you see here, where it's going to be all white. As time goes by, that is going to become transparent. The white part is the salt. The transparent part is water forming, liquid water forming. All right, hopefully the video is working for everybody. And we see deliquescence forming right in front of your eyes. This salt is uptaking water and entering into solution. We have liquid formation. Notice that it takes a really long time for all of the salt to enter solution. And in fact, this was a several hours worth of a video. But under the appropriate combination of temperature and humidity, oh no, everything froze. There you go. Under the appropriate temperature and relative humidity, somewhere in that petri dish, you immediately were able to form a liquid. However, experiments under lower temperatures have shown that it's not always completely instantaneous, meaning just because you're above the right temperature and humidity, it will take time for one of these salt grains somewhere to enter solution. And it seems like that's going to be dependent on temperature, humidity, and grain size. There is a paper that suggests that we have observed potential evidence for deliquescence on the surface of Mars, which is shown here in this figure, where they're interpreting the droplets that you see on the Phoenix Lander strut as evidence for deliquescent salts forming these liquid water droplets on the strut. However, that's still contentious and it's not completely agreed upon. But nevertheless, the reason that we think deliquescence is a likely process on the surface of Mars is because as we've done experiments, we see face diagram, the black deliquescence relative humidity, and the light blue squares are the experimental data that were used to build that semi-empirical model, specifically for calcium perchlorate. So from a theoretical perspective, so long as the conditions are between that black and blue line, so that dark gray zone, a liquid would be expected to form. Once you surpass the black line and you go below the blue line, then the idea is that you no longer have a brine. I've shown that within that lighter gray area, you have to keep going past the black line to actually form the liquid. And you have to, sorry, my computer, I think, just froze. So you have to pass the black line up until the cyan land to finally get rid of the liquid, and you have to pass the red line to finally get rid of the liquid. And the red line over here is the efflorescence relative humidity. There's also some experiments that are suggesting that you could have supercooling in the lab settings, and you could form a stable brine all the way down to 186 Kelvin. So this is a broad region of phase space where you could have brine formation. And we know this phase space also corresponds to when appropriate Mars relevant combinations of humidity and temperature. So these are likely processes that may be occurring on the surface of Mars that we need to better understand. Oh no, I am definitely freezing.
Ed, you're
Someone
freezing
confirm
our
if
end
people
too,
can
so
actually
if
still hear me.
you can shut off your video maybe.
The entire app just froze.
Ed, would you like us to share your slides? I don't know if he's hearing us. Thank you.
Hi everyone, this is Germán Martinez, and Edgar is texting me saying that his computer froze.
If y'all can hear me, I'm asking Germán to let you know that everything's frozen, so I can't respond.
Sorry, everyone. We're trying to figure out this technical difficulty. Ed, are you back online? Okay, so what time? Okay, so what we're gonna do is go ahead and take a 10-minute break, try to get back on schedule, but we'll give Ed a chance to finish up when we get back from our break and see if we can